Hello everyone. Parametric modeling is a method to define various input values using parameters. This method allows you to reduce modeling time and automate the process to change the input values. This seminar introduces how to use parametric value and parametric point for parametric modeling in RecurDyn. A lot of RecurDyn expert users are frequently using parametric value and parametric point. Through this seminar, I hope that you will also be able to take the first step to proficiently use this parametric value and parametric point. The contents of this seminar are as follows. First, what are parametric value and parametric point, and how to use parametric value and parametric point will be introduced in detail. After that, I will talk about why you should use parametric value and parametric point. I will also explain Parametric Connector, which is used when you are using parametric value and parametric point. Finally, I will wrap up the seminar after introducing scalability using PV and PP. First, let me explain what parametric value and parametric point are. Parametric is the adjective form of parameter. It means parametric value is the scalar value type of parameter. And parametric point is 3D vector type of parameter. For example, let's say we have two variables, which are a and b. Let's assume that a equals 1000 and b equals 100 are defined. Different spring stiffnesses or body radii can be defined using these a and b parameters. For example, you can define stiffness as a and the radius of body as b. In this model, the radii of all three spheres are defined as PV2_radius. The stiffness of the three springs is all defined as PV1_stiffness. At this time, when modifying the parametric values, PV1_stiffness or PV2_radius, it is possible to change the stiffness of the springs or the radii of the spheres using these values at once. The input values defined as parametric values are converted to numbers before starting a simulation for the RecurDyn solver to use numbers. When running a simulation in RecurDyn, the 3D model data is first written into a text file called RMD. After that, the RecurDyn solver uses this RMD file as an input file. As you can see, K, corresponding to the stiffness of spring, is all converted to 1000 in RMD file. First, let me show you a demo video that simply defines the radius of a sphere as a parametric value. First of all, create a sphere and enter the body edit mode. Open the Properties dialog box and click the PV button to open the Parametric Value dialog box. After that, create one parametric value and the radius set to be 5000. Now click OK and the radius will be changed to 5000. Open the Parametric Value dialog box again, change the value to 10,000. Then, you will see the radius of the sphere is changed to 10,000. Now let's focus on parametric value. Since the wording parametric value is too long to pronounce, let's call it PV from now on. Similarly, parametric point will be called PP. Before explaining PV, I would like to explain what subentity is. Entities that can be pre-created and also reused are called subentities in RecurDyn. In RecurDyn, there are various subentities such as PV, PP, spline, expression, and more. Among the various subentities, PV, PP, and Parametric Value Connector and Parametric Point Connector will be introduced in this session. For your reference, string is an entity, also called parametric string, but it will not be covered in this seminar. PV, aka parametric value, is used mostly for reuse. It is literally a subentity used as a parameter. For example, let's say PV1_radius has been defined as 150. This PV1_radius can be used for multiple bodies and joints. When changing this PV1_radius from 150 to another value, the values of multiple entities using 150 will be all changed at once. PV and PP to be introduced later can be defined in each of model, subsystem, and body independently. PV1, PV2, PV3 can be defined in Model 1. And PV1, PV2, PV3 can also be defined in Subsystem 1 or in Body 1. Of course, it is possible to give the completely different names to them. PV can be used for various parameters. Most of them in RecurDyn support PV. All the parameters with the PV button support PV. For example, PV can be used for simulation parameters, such as maximum time step or initial time step. To start using PV, click the PV button to display the PV dialog box. After that, select the desired PV in the PV dialog box. Otherwise, you need to create a new one. Click OK to set the specified PV to the parameter. If you already know the PV name, you can type it directly without displaying the PV dialog box. PV can be created in the PV dialog box. There are various ways to create PVs. The first way is to enter a number. You can define PV1 as a number such as 100 or 200, which is the most basic way. In addition to this, PVs can be defined using other PVs. If PV2 is set to PV1, PV2 has the same value as PV1. You can also set PV3 to be twice that of PV1. Like PV4, it is also possible to set PV as the median value between PV2 and PV3. PV can be also defined using expression. After clicking the E button, you can specify the desired expression, such as x1 in the expression dialog box. Then, as you see here, PV5 can be set to x1. However, if a PV is defined as an expression, note that the PV is not a value that changes with time, but the value of the initial state, which is used as a constant. Now, let me show you a few demos about PV. The first demo shows how to set spring stiffness to PV. First, create two PVs. Then create a sphere and a spring. After that, set the spring stiffness to PV1. Now, enter the body edit mode of the sphere. Set radius to PV2 at Model 2. At Model 2 typed after PV2 means that PV2 defined in the Model 2 including this body will be used. The radius is now 100, which is the value of PV2. Finally, let's use the same PV for both spheres. First, change PV2 to 200 in the model, which will change the radius of the sphere. And create one more sphere. At this time, enter PV2 in the command window to set PV as the radius. After that, if you change PV2 to 100, you can see that the radii of both spheres change accordingly. So far, I have introduced what PV is and how to use it. This time, I will explain in what cases PV is used. First, multiple geometries can be defined using PVs. You can set the length, thickness, radius, etc. to PVs. In particular, the radii of multiple spheres, the lengths of multiple boxes, and others can be defined and managed using the same PV. Next, correlated variables can be managed using PVs. If there are 3 spheres and the ratio of radii is 1 to 2 to 3, the PV can be defined as follows. Set each radius to PV1, PV2, PV3. Then, if only PV1 is changed, PV2 and PV3 are automatically changed. In this case, the ratio 1 to 2 to 3 is maintained accordingly. Not only shapes but also material properties can be set and changed using PVs. You can set the stiffness and friction coefficient of springs or contacts to PVs. After setting all the stiffness of several springs to PV1, if only PV1 is modified, stiffness of multiple springs are all changed. The Euler angle of a body can also be defined as PV. In this case, parametric point cannot be used for Euler angle. Instead, each component of Euler angle can be defined as a PV or a number. At this time, remember that the unit of PV is always treated as radian. From the next page, let me show you a demo video of how to use PV. As you can see, there are 3 PVs. PV2 is twice that of PV1, and PV3 is 3 times that of PV1. And the radius of each sphere is set to PV1, PV2, PV3 in turn. If you change PV1 to 50, the radii of all 3 spheres are changed accordingly. Similarly, if you change PV1 to 200, the radii of the 3 spheres change to 200, 400, and 600 accordingly. This time, let's check the value defined as PV with a text editor. First, set the stiffness of both springs to PV1. Now, let me export the RMD file for this model. First, let's check the stiffness of these 2 springs. After exporting the RMD file, open it with a text editor. You can see the stiffnesses of both springs are 200. Next, change the PV to 500. And export the RMD file again. As you can see, the stiffness of both springs has been changed from 200 to 500. From now on, let me explain parametric point, which is quite similar to parametric value. Let me call the parametric point PP. PV is a scalar value while PP is a 3D vector type parameter. It is mainly used to specify coordinates. For example, after defining the positions of multiple bodies as PP, their positions will be changed at once when changing pages. PP has an input called relative to. Let me explain what this is later. In the figure on the right, PP1 is used as the position of the upper 2 body endpoints. Therefore, if you change the position of PP1, the endpoints of the 2 bodies defined as PP1 move at the same time, while maintaining the connection of the 2 bodies. Parametric point can be defined for each model, subsystem, and body independently. Parametric point can be defined in various ways. You can usually enter numbers such as 100, 500, 300. By the way, if you input only 100 in the point section, 0, 0 are automatically added in the component section, displaying 100, 0, 0. Similarly, if you input only 300, 200, 0 will be automatically added, displaying 300, 200, 0 in the component section. PP can also be defined using PVs. A predefined PV can be used for each X, Y, Z component of a PP. It is also possible to use formulas with PVs. As you can see, PV1 and PV3 are used for X, Y components of PP4. The median value between PV2 and PV3 is used for Y component of PP5. PPs can also be used to define another PP. In this case, the way you enter is pp.x, pp.y, pp.z. You can see that pp3.x and pp4.z were used for pp6, and both values are 300. Finally, it is time to explain relative to. If you input a marker in the relative to field in the dialog box, PP is created at the relative position from the marker's position, which is considered as an origin. In this example, the position of the marker is 500, minus 500, 0, and the input points are 200, 200, minus 50. As a result, the actual position of PP7 is 700, minus 300, minus 50. I tell you that this is a very useful method. Now, let me show you a demo about PP. There are several ways to create a parametric point. Open the PP dialog box, click the PT button, and then click the desired point. Or you can click the PT button and enter the desired position in the command window directly. Of course, you directly enter the position in the dialog box. As I mentioned earlier, if you do not enter some of X, Y, and Z components, they automatically become 0. As you can see, if you input only minus 200 and press the apply button, PP is created at minus 200, 0, 0. And if you enter minus 100, minus 500, the Z coordinate is automatically entered as 0, and PP is created at minus 100, minus 500, 0. This time, let's use PP in body edit mode. As you can see, PP1 is defined in the body edit mode. First, create a sphere and enter PP1 as an origin in the command window. This will create a sphere centered on PP1. When changing PP1, you can see that the origin of the sphere changes accordingly. This time, let me start with existing two PPs, create a cylinder and select PP1 and PP2 respectively for 2 points. In the dialog box, you can see that the 2 points are set to PP1 and PP2 respectively. This time, create another cylinder. After that, in the dialog box, click the PT button of the second point of the second cylinder, and then select PP2. Unlike PV, the PP dialog box is not displayed. Instead, PP2 can be selected directly from the screen. Then, open the PP dialog box to change the position of PP2. You can see that the joints of both cylinders move along with PP2's movement. This time, let me explain when to use PP. PP is usually used to specify the position of a body or a joint, such as the center of a body or the end point of a cylinder. It could be quite effectively used when specifying a relative position using relative to field. As you can see, when body 2 is located at 500, 0, 0 from the end point of the cylinder, it can be defined as PP1. It is also possible to define a body located at the midpoint of two bodies using a formula. It is also possible to define only specific components among X, Y, and Z as parameters. When creating PP, you can define the specific components as PV, and the rest as constants. PP is also used to define symmetric coordinates. As you can see, if the X coordinates of PP1 and PP2 are expressed as PV1 and minus PV1 respectively, they can be used for the symmetric coordinates with respect to the y-axis. In this way, you can define bodies or joints at the symmetric positions. The relative to field allows you to define the symmetric position with respect to a specific marker. As shown in the figure, you can define a point that is symmetric with respect to marker 1. Marker 1 is located at 200, 0, 0. Therefore, PP1 is located at 500, 0, 0, and PP2 is located at -100, 0, 0. Which shows they are symmetric with respect to marker 1. However, in the case of PP3 on the far left, the x-coordinate is -pp1.x. Since the x-coordinate of pp1 is 500, minus pp1.x becomes -500. As it is -500 relative to marker 1, it is located at -300, 0, 0. PP can also be used for the orientation of a body. I explained earlier that Euler angle type does not support PP. When using coordinate type, master and slave points can be defined as PPs. With the coordinate type, the orientation is determined by the relative positions of origin, master, and slave point. Therefore, if the origin is changed, the orientation is accordingly changed. To avoid this kind of change, it is very convenient when defining the point at infinity as PP for the master or slave point. Let me explain it using a demo video. If the z-axis and x-axis are defined using master and slave, the orientation will be changed when changing the origin. However, if the axis direction is specified using an infinity point, the direction of master or slave is maintained even though the origin is changed. If you want to keep only the z-axis constant, for the revolute joint or translational joint, you can set only the master point to the infinite z-axis. So far, I have explained how to define and when to use PP. Here, let me introduce one more way to define PV before moving on to the next session. PP can be used to define PV. You can use the pp.x, pp.y, or pp.z mentioned earlier. If PV6 is defined as pp1.x, PV6 becomes the x value of pp1 equal to 100. For PV7, pp1.x and pp4.z are used, and it equals to 700. PV8 is the distance between the y and z coordinates of pp2 and pp3, which equals 200. So far, I have explained parametric value and parametric point. In this session, let me explain why we need to use parametric value and parametric point, and the advantages of using PV and PP. With PV and PP, you can improve the efficiency of managing multiple parameters. In RecurDyn, you can certainly use the multi-select function to change the parameters of multiple entities at once. However, if using PV and PP, you simply need to change the PV, PP in their dialog box without multi-selection. As a result, mistakes can be significantly reduced. Similarly, you can manage frequently used parameters or points by setting them to PV or PP. For example, after setting all the hard points of a vehicle model to PP, you can manage them in the PP dialog box. It is also possible to edit different entities at once, such as radius, contact parameter, joint friction, and others in the PV and PP dialog boxes. Even with multi-select, it is rather cumbersome to edit different entities at once. However, using PV and PP makes it much easier. At this time, you better give PV and PP the intuitive names. In this seminar, I usually use the names such as PV1, PV2, or PP1. However, in practice, it is recommended to use more intuitive names that users can tell by them easily. In RecurDyn, in order to edit the body's radius, the box's length, or others, you must enter the body edit mode one by one. However, using PV and PP lets you edit them without entering the body edit mode. I showed the demo in the previous demo video. The input such as PV1 at Model 1 was used in the demo. However, PV and PP in the different subsystems cannot be used in this way. In this case, you better use Parametric Connector, which will be explained later. Lastly, let me introduce import-export of PV and PP. It is possible to export PVs and PPs to a separate text file and to import them to other models for reuse. In other words, the frequently used PVs and PPs can be exported to be used as a library. You can export or import PV and PP lists in the PV PP dialog box. As you can see, it is exported in text format. It is also possible to import this text file after modifying it with a text editor. When importing a text file, if there is already a PV or PP under the same name, the value is updated. Let's try to export PVs. Save the RPV file by clicking the Export button in the PV dialog box. Now let's try to import PVs. First, create a new model. And after opening the PV dialog box again, click the Import button to import the RPV file. Then you can see that PVs and RPV file are added to the list. There is one more way to export or import PVs and PPs. Use the Export and Import of the Subentity menu. This function exports all subentities other than PV and PP in XML format. It is also possible to import an XML file after modifying it. If there is a subentity under the same name, the entity's value is updated. It is more recommended to use this method than the export and import of PV and PP introduced earlier. This time, let's try to import and export the subentities. First, if you click the Export button, all the subentities existing in the current mode are displayed. If this checkbox is unchecked, the corresponding entity is not exported. The subentities checked in this dialog box are saved as XML files. Now let's create a new model. When clicking the Import button, the list of subentities stored in XML is displayed. Here again, you can select the entities to import by clicking the checkbox. And when clicking the Import button, the checked entities are imported. By displaying the PV, PP, and expression dialog boxes, you can see that the imported subentities have been successfully added. So far, I have explained why using PV and PP is important. And I also introduced how to export or import PVs and PPs. I will end this session here and continue it in the next one. So far, I have explained Parametric Value and Parametric Point. Now let me introduce Parametric Connector. Previously, I have explained that PVs and PPs exist in each model, subsystem, or body independently. By the way, in order to edit the value of PV1 in Body 2 and Subsystem 1 of the top-level model, you need to enter the body and subsystem edit mode and edit them one by one, which is quite troublesome. Parametric Connector is a special subentity that removes the time-consuming process. You can change PVs and PPs in the child body or child subsystem from parent model. Let's say that PV2 in Body 2 is 100 and PV2 in Subsystem 1 is 200. At this time, create a Parametric Value connector called PVC1. Then, connect PV2 in Body 2 and PV2 in Subsystem 1 to PVC1. Set the value of PVC1 to 3. This will change both PV2 in Body 2 connected to PVC1 and PV2 in Subsystem 1 to 3. Please note that PV or PP connected to PVC or PPC cannot be changed in the PV or PP dialog box. I will introduce how to use PVC with a demo video. There are two spheres. The sphere on the left is defined inside the subsystem. PV2 defined in the subsystem is defined as 200 and it uses PV2 as its radius. The case of sphere on the right is the same as the previous one. PV2 in the body was used for the radius and PV2 equals 100. Now let's create a PVC. First, create one PVC and enter 3. After clicking the REFS button, select both PV2S in subsystem 1 and body 2. REFS marked as 2 means that 2 PVs are connected to the PVC. When clicking the Apply button, the values of the connected PVs are changed to 3. In other words, the radius of both spheres changes to 3. Let me try to change the PVC to 50. Then both PVs will become 50, and the radii of the spheres will also be changed to 50. If you change the PVC to 100, the radii of all spheres is changed to 100. As you can see, after clicking the REFS button, the PVC dialog box is displayed. And all PVs belonging to various subsystems and bodies are shown. After checking the PVs to be connected, click the Load button. And if you use the search function, you can find the PVs which include the specified text in the name. Use this function when there are many existing PVs or PPs. In order to use this function conveniently, use the same name for the PVs and PPs that will be connected to Parametric Connector. So far, I have introduced Parametric Connector. Even though I mainly focused on Parametric Value Connector and PVC, the usage of PPC is the same. Finally, this is the last session. I will introduce the scalability of RecurDyn using PV and PP before finalizing this seminar. Modeling with PV and PP could be considered as parametric modeling. These parametric models are practical when performing DOE or optimization in RecurDyn. For DOE or optimization, it is necessary to define the design variables. In RecurDyn, the design variables can be defined using PV. In other words, modeling using PV must be preceded for DOE or optimization of RecurDyn models. Here is one more thing. There is an add-on tool called Parameter Designer for RecurDyn. It allows you to modify the RecurDyn models using Excel, and this tool also uses PV and PP. First, let me explain DOE in more detail. DOE stands for Design of Experiment. There is an analysis type called DOE in RecurDyn. To use this analysis, you need to define PVs as design variables. And we need to decide how many segments this needs to be divided into. If a PV is defined as design variable, specify the range of design variable first, and decide how many segments this needs to be divided into. For example, PV_control_angle is specified as a minimum of 12 and a maximum of 60. If this value is divided into 4 segments, the values would be 12, 28, 44, and 60. You can set the other 2 PVs in the same way. Since the number of values is 4, for each PV, the total number of cases is 64. DOE allows RecurDyn to perform simulations for these 64 cases while automatically updating the PVs. It is also possible to perform simulations by extracting only the necessary number of cases rather than all cases. The purpose of DOE analysis is to easily simulate the numerous cases to find the optimal case out of the results. And PVs are certainly required in this process. Next, let me introduce Parameter Designer. This is an add-on tool for RecurDyn which can be downloaded from the following link. An installation guide for Parameter Designer and its tutorials are also included. Here, I will introduce it briefly with a demo video and wrap up this seminar. Let me show you how to use Parameter Designer. In this model, 1 PV and 7 PPs are used for the spring. You can export PV, PP, and other information as an Excel file using Parameter Designer. The information of PV and PP is written in the Excel file. Let me change the PV from 10 to 30 in the Excel. And modify PP as well. Then, save and import the file. As you can see, the values modified in the Excel file are applied to the model, so that the PV used for spring is changed to 30. Now, let's try to modify PV and PP a bit in Excel. After saving and importing the file, you can see that the model is changed accordingly. Now I have completed introducing all the contents prepared. Let's take a look at what I have covered in this seminar. First, PV and PP were introduced. What are PV and PP? How to create PV and PP? Why are PV and PP important? I also introduced PVC and PPC. What are PVC and PPC? How to use PVC and PPC? Lastly, I briefly introduced the scalability using PV and PP, DOE and Parameter Designer. The seminars regarding DOE and Parameter Designer are currently at a preparatory stage. Please watch them for more details. This is the end of this seminar. The more proficiently you can use PV and PP, the more efficient RecurDyn modeling becomes. In fact, RecurDyn expert users are working with dozens or hundreds of PVs and PPs in their model. I think it would be great if you make it a routine to define values or points as PV and PP. I recommend to try to create your own PVs, PPs, PVC and PPC as I introduced in this seminar. If you have any questions, post them in the forum bulletin board on the Function Bay technical site. Thank you.